Lads, what we have here is a standard video game called Angry Birds that most people are familiar with. Now, if I make this guy fly, we can see that he undergoes a sort of an N-shaped curve. This N-shaped curve can be modelled upon a minus x squared, a minus quadratic. Okay. So if I show you the flight path, we can see now that the bird in question actually undergoes the U-shaped curve. Okay. If I show you the full quadratic, it's a full N-shaped curve. But I don't need to show you the full quadratic, right? Now, if I get rid of the background, we can now represent this flight path using XY coordinates, okay? Now, a question might be, how fast is the Angry Bird actually going? Okay? At any given point. So, its velocity at the start is going upwards. Would you agree that it's going vertically upwards? Yeah. Up to the right. This is a positive slope, therefore the Angry Bird is ascending. Okay? When he reaches the top, he plateaus and he has no slope. This means for a momentary instance, his velocity going upwards is going to be zero. And then all of a sudden comes back down. Now, what happens next is I show you a point here. I'm going to show you a second point. Okay? Now, if we were to imagine the slope between these 2 points, okay? And this is what we were doing earlier. Okay. Now, if I was to bring the bird back to the middle of these two, or sorry, to one of these points here, this point here, in fact, okay, and I have to show you its tangent. The Angry Bird is currently going up with the blue velocity. Do you understand? That's its actual speed. Is the slope of that line there. Now, what happens is, as I bring this point closer and closer to the other point, what happens? Eventually, it's going to be the same as the tangent or the velocity of the Angry Bird. Okay. Now, to get the slope, okay, you'd get the difference of the y's over the difference of the x's. Okay. And then what happened is you'd eventually go so close that the difference of the y's over the difference of the x's is the same as that of the tangent. Okay? Now, what we can do next is we can show first principle labels. Okay? Now, first principle labels is this. Now, let me explain what this means. Okay? A means the first point. F of A means the y value of the first point. A plus H. H represents the gap in between these two. Sorry, it's covering up actually. I just need to probably. It has covered up, hasn't it? So where's the flight path? Just get rid of this for 1 second.
No, it's there. It's just that it didn't go all the way.
The bird is still there.
Oh, I got you. Okay. I understand. Okay. So guys, what happens is the Angry Bird continues its path, right? And we're going to use the blue dot to represent the Angry Bird at any given point on this diagram, okay? So, if I show you the first principle labels, what this H represents is a small change in the graph. Okay, so if I bring it back to the original, I'm going to bring it back just to a regular function, okay? So a regular function would be like this. If I had f of x equals minus x squared, okay? Which will be this one here. Y equals minus x squared. Okay, and we can see that this is very similar to the n-shaped function used. Okay, now what I can also do here is I can get any point on this graph. Okay, any point on this graph, and I'll probably take a snapshot of this. Okay, any point on this graph is represented by two things. Any point on this graph is represented by x is the x coordinate, and f of x is the y coordinate. Now, if I do this, where I add a small function, well, if I add a small bit to the right, what happens is I can say what happens for x plus a, or x plus anything, or for example, I can change this completely to. I can change it to a and a plus h. I can say f of a equals a squared. So the function is now expressed not in terms of x, but in terms of a. Now what I can say here is, what happens if that's a and f of a. What happens if I say add a tiny bit onto h? So add a tiny bit here. Do you understand? So I'm adding a tiny amount to the right, and I want to find what point is located a tiny amount to the right. I then have to find out what is the value of that function at that point, and that will bring me back to this part here, where I can say that this is one point. One point is a plus h, f of a plus h. The other point is a, f of a. Okay? And then what we can do next is we can show what the rate of change is. Okay? And the rate of change is basically going to be, remember what we said, the slope. It's the slope, the top part, minus the difference of the y's over the difference of the x's. Now look what happens when I do the difference of the y's over the difference of the x's. x2, y2, y2, x2, x1, y1. Now look what happens. It's going to be f of a plus h minus f of a all over a plus h minus a. The a's cancel, don't they? And I get f of a plus h minus f of a all over h. Now, once again, a just represents x, doesn't it? So technically it's f of x plus h minus f of x all over h. And what does h represent again? H represents the tiny distance, the tiny difference in values of the x's. Do you understand? And what we said earlier is the closer they are together, the more accurately they get the slope of the tangent. Okay? So what this means here, if you just we'll look back at the Angry Bird part, right? So what this means that the rate of change between the two of these. Now look what happens when I change the rate of change here. Okay, I'm going to change this point using this move. Okay, and look what happens as I move it down. Okay, it gets smaller and smaller and smaller, and then eventually it matches the tangent. Now, what I'm going to show you is what's called the secant workouts. What I'd get from this slope from blue to the actual speed of the Angry Bird right now is what? It's 1.28. It's 1.28 meters per second, because the y-axis is meters and the x-axis is just like time. Okay. Now, what happens next, guys, is look what happens when I change this. Look at the numbers. See the numbers? 3.88, 4. That's its slope, and its slope is changing. And what happens, and see this value here? That's its actual speed. Now look what happens when the value gets smaller and smaller and smaller. What's going to happen? It's going to change eventually into 1.28. It gets really, really close, and that's the end of it. Now see this limit as h approaches 0. What does that mean? It means you make the gap smaller and smaller and smaller. Right now, h is quite big. There's a big gap between x and x plus h. It's the distance going left to right. And what happens when I make this distance left to right very close to 0? What happens? It eventually becomes the slope. Now look at this, guys, okay? So basically, if I put the limit of this as h approaches 0, this will eventually become the slope of the tangent. Now, this brings me to the differentiation that you already know. Okay? So an example would be, definition. The slope of a tangent is f of x plus h minus f of x all over h, where this represents where this represents 2 points on the graph. This is x and f of x. This one here is x plus h and f of x plus h, and h represents the horizontal distance between x and x plus h. When we make this very small, what happens is they get closer and closer together, and then eventually represent the slope of the tangent. So when you're differentiating from first principles, what you're going to do is the following 4 steps. Okay? These 4 steps here. Now, what we're going to do is we're going to differentiate some functions. And let me show you now. We previously accepted that when we differentiate these, all of us already know the answers. We know that this one is 8. We know that this one is 2x. We know that this one here is 2x minus 2. Let me explain why. Okay? So, what happens now, guys, is we write down what f of x is. F of x is 8x plus 3. We're going to differentiate this function from first principles. Find out what f of x plus h is. How do you find out what f of x plus h is? 8 times, what is it? X plus h plus 3, which is 8x plus 8h plus 3. Next step, take f of x away from f of x plus h, and look what happens. 8x plus 8h plus 3 minus 8x. What's left over?
8h.
Sorry?
8h plus 3.
8h plus 3.
I'll have to take away 3 as well.
Oh, there's a 3 there as well. Yeah. So,
That'll be minus 3.
and it'll be a minus 3 when you multiply it in, so the 3 is gone as well. Yeah, AH. Now, third step after that, divide by H. The H on the bottom will always have to disappear. And then finally, after this, your limit of H goes to 0. And because this has no 0, it doesn't matter, and this means it represents 8. When you differentiate this function, the answer will always be 8. Let's try a quadratic one. Okay, we'll try number 5. Okay, same steps again for number 5. Now, this used to be on the Leaving Cert ordinary course, so you guys are well capable of doing these quite easily, okay? X squared plus 6, what's the next one then? X plus h squared plus 6, okay? And then finally, what happens here is going to be, it's going to be x squared plus 2hx plus h squared plus 6. One of them minus the other one, which is going to be x squared, I'll colour code them. X squared plus 2hx plus h squared plus 6 minus, so it's going to be minus x squared plus 6, which is minus x squared minus 6. What cancels? X squared cancels, and look what we have left over. 2hx plus h squared all over h. Cancel. Cancel, cancel. 2x plus h. When h approaches 0, it's going to be 2x. And that's what happened when you differentiated. So all of this is linking back into this curve being this gap being really small, and the derivative gives us the formula for the slope of the tangent. Okay? Gives us the formula for the slope of the tangent. I'm going to do one more of them, and then I'm going to put it in context for the slope. Okay? Last one. I'll do the big one, guys. I'll do the big one. The big one is number 12. Okay? Now, what is our answer before we begin? We already know the answer to differentiation. If you don't get 6x minus 5, you've gone wrong. Now look at this. Same steps again. Nothing changes. So much so that I can basically rub out everything from the last question. Now look at this. It's going to be 3x squared minus 5x plus 12. Step 2. X plus h. Now what I'm going to do is I'm going to do 3 times x plus h squared up here, just to save space. It's going to be 3 times x squared plus 2hx plus h squared. It's going to get me 3x squared plus 6hx plus 3h squared. Okay, happy enough with that? And then there's going to be it's going to be minus 5 into x plus h. What's that going to be? Minus 5x minus 5, and then the 12 at the end. We can't tidy that up at all. Now guys, what we're going to do next is we're going to put all of this in. Our 3x squared plus 6hx plus 3h squared minus 5x minus 5h plus 12. This represents which part of the function? Represents the x plus h. Now to put in the f of x part. Minus 3x squared minus 5x plus 12. Turns into minus 3x squared plus 5x minus 12. Look what cancels. 12 cancels, 5x cancels, 3x squared cancels. Everything that's left usually always has an h in it. Now, we have to divide this answer by h. Cancel, 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 cancel. We're left with 6x plus 3h minus 5. And this here will give me, 6x minus 5 because h turns to 0. Now let me explain. This 6x minus 5 gives you the slope of the tangent at any point on this graph. Let me draw this graph out for you and put this in context. Okay, can somebody call me out this equation please? The equation of the question I just did. It's 3x squared, what else is there?
Minus 5x plus 12.
Okay, so y equals 3x squared minus 5x, what is it? Plus 12. Now look at this guys, what type of function are we expecting? U-shaped. Okay, now it's a big U-shaped I think. There we are. Now, look at this. Here it is here. And I can probably actually, now that I've found where it is, yeah, there we go. Okay, look at this guys, okay? Now, what I would do with you guys is, I say, here's the function. It has non-stop tangents in it, doesn't it? Like, it has different tangents at different points. So, for example, if I was to take a snapshot of this, like so, what would happen is, it's like that graph we've seen at the start of the chapter, okay? Where basically it has different tangents at different points. So for example, right, this one here, this could be a tangent at that point there. This one here is a tangent at this point here. And this one here, I don't know where it's going to be a tangent yet. Around there, yeah? Do you see the way there's so many different tangents at so many different points? Now, what the great thing about this is, this function here is that it will give you the slope of any tangent at any point. So for example, if I wanted, I do need the x-axis here, so I'll just have to take another one. So, if I wanted to find out the slope at x equals minus 1, for example, okay? So, if I wanted to find the slope of the tangent of x equals minus 1. So, x equals minus 1 is which point on the graph, guys? It's minus 1, minus 1, 20. Now, if I want to find the slope is the first derivative. The slope is 6x minus 5. Now, what is the x value then? The x value is minus 1. The slope of this line is going to be 6 times minus 1 minus 5. The slope is minus 11. This means that this graph is changing at minus 11. If this was distance and the x-axis was time, it would be changing at minus 11 meters per second. Now, some of you might go, well, how do you find the equation of the line? How do you draw that in? to find the equation of the line, and this is what we'll be moving on later, is the equation of a line is y minus y1 equals m into x minus x1. Okay, now look at this. Y minus what? 20 equals minus 11 into x plus 1. 11x plus y minus 11x minus 11. 11x plus y, bring the minus 11 over, comes plus 11 plus 9 equals 0. Will somebody remember off this one off by heart for me? This equation of a line. Okay, now look what happens when I put it in. Somebody predict what you're expecting to happen. 11x plus y, what is it? Plus 9. Now look what happens. Up, is it minus 9, lads?
Yes.
Sorry, it should be minus 9, not plus 9, minus 9. Now, what I'm expecting to happen is, I'm expecting to get a perfect tangent at the point 120. Let's try this again. What's it? 11x plus y minus 9 equals 0. And look, there's your perfect tangent at that point there. The first derivative will get you the slope of the tangent at any point you want. Therefore, you can find the rate of change. And that's how differentiation works.